Okay, let's get started with class today. We're pretty much done with section 15.2. This is a reminder, like 15.2 is just looking at double integrals over more general regions. Like we knew how to do them on rectangles and now we know how to do them at least over these kinds of regions, right? Where it's like vertically or horizontally simple. There's one thing that I haven't covered yet from this section, and that's going to be on average value. And so I kind of discussed this a little bit yesterday, but I want to go through an actual example. Before I continue, does anyone need the notes? Okay. Yeah, so we saw that you can compute the average value of a function by looking at the integral in Calculus 2. So maybe you took it last semester. So we have something that looks like this. And one way of rethinking this average value equation is the following. You can rewrite this as being equal to the integral from a to b of f of x dx over the integral of a, or integral from a to b of just 1 dx, right? If you took this integral, it's the same thing as this doing b minus a, right? So really this average value function, or this average value of your function, is just like the quotient of this integral over this integral. And this is an important idea to keep in mind, right? We didn't really say much about it in Calculus 1 or 2, but this integral really just gives you the length of your interval. And so you can think about what ends up happening if we take this same idea and we bring it into the second dimension, right? So if we were to do the exact same thing, say we have like this square or like this rectangle. I don't really, I should have dedicated some writing to this so that way you don't have to like write it out yourself. But this is from A to B, and say this is like from C to D, like y is equal to C, D is equal, or y is equal to C to y is equal to D. Right, if you had this kind of rectangle, the area of this rectangle is going to be equal to B minus A multiplied by D minus C. And you can see that this is the exact same thing as taking the integral or the double integral from A to B and then doing the integral from C to D, right, of just 1 dA. Right, so the area of this region can be expressed as this double integral of 1, right? And so this area equation, this average value function, sorry, I'm like misspeaking. The average value of this multivariable function on a domain D, we said yesterday that it has the following form, right? It's 1 over the area of your domain times this double integral over f. Sometimes it's hard to find what this area is going to be. Like sometimes you're given a rectangle, but sometimes you're given like an ellipse or a circle or some weird shape like a bean or something like this. It kind of looks like a bean. And he's like, how would I find the area of that off the top of my head? It would probably be easier to think in terms of integration, right? So you can rethink of this equation as being this double integral over the multivariable function f of xy dA over the double integral over d of just 1 dA. So like this area, again, can just be written as this double integral. And we'll see later on, like when we introduce triple integrals, that you can consider volume or view volume as just being the triple integral of 1, right? So we'll talk about that later on, but really it just comes from this idea here, right? If you do b minus a times d minus c, if you were to integrate this with respect to x, that would give you a b minus a. That would be a constant. You could bring it outside, integrate with respect to y. That would give you a d minus c. And so this ends up being the integral, and it also happens to be the area. Okay, so that's something to keep in mind. This is an important idea that will show up later on in this class. Okay, and so going through an actual example where we don't actually have to use this interpretation, but we'll use it later on. So in this example, it tells you that an architect needs to know the average height given by h bar. So like there's an overline over the h of the ceiling of a pagoda whose base d is the square from -4 to 4 crossed with -4 to 4. That's this box right here. That's what it's describing by this product of intervals. And then the roof of the graph, i.e. this surface here, I'm highlighting in red. This is given by h of xy is equal to 32 minus x squared minus y squared. Our distance is going to be given in feet. And so what it wants you to do is it wants you to find the average height of this pagoda that it was describing. And so you just use this formula that's given to you, right? So it ultimately just turns into computing a double integral. So the first thing we do is we have that this h bar, we can just write this out as being 1. This is the formula that we're going to be using. Where I'll describe, when I say D, I mean like this square right here. That's your domain. And then this is going to be the double integral over D of h of xy dA. And so we can start filling in these quantities, right? So the area of D, right? It's just asking you to find the area of your domain, which is this square. So this square, it's 8 units by 8 units. So we know the area is going to be 8 times 8, which is 1 over 64. And then we need to think about the bounds of integration. Luckily for us, we're just integrating over a square. So you don't have to do anything fancy with respect to writing out the bounds in terms of other functions. And so we know the bounds of integration are just given by -4 to 4, -4 to 4 for both x and y. And then we're given h of xy is 32 minus x squared minus y squared. And then I'm just going to integrate with respect to y first, and then with respect to x. This one, it doesn't really make a difference which one you integrate first. They're both the same difficulty, I would say. So now it's just a matter of integrating this. And this is kind of the easy part, right? It depends on the function, but this one is like, you're given a polynomial, so it's pretty easy to work with. So this is 1 over 64 from -4 to 4. Integrating with respect to y gives you 32y minus x squared times y minus y cubed over 3. And then this goes from -4 to 4 dx. So you plug in 4, you plug in -4, subtract the 2, and you see what happens. So I'm just going to write out what this ends up looking like. So this ends up being 1 over 64 times this integral from -4 to 4. And so this ends up being, from my notes, it says it ends up being 640 over 3 minus 8x squared dx. Right, all I'm doing is just plugging in at y is equal to 4, subtracting what you get when you plug in y is equal to -4. So nothing too crazy going on there. And then it's just a matter of integrating this with respect to x. Again, it's a polynomial, so the integral itself isn't going to be that bad. So this is going to be 1 over 64. And then you'll have a 64 over 3x minus 8 over 3x cubed. This goes from -4 to 4. And then, okay, so you just plug in the numbers again. It's not super interesting. So this ends up being 1 over 64. If you plug in x is equal to 4 and subtract by what you get when you plug in x is equal to -4, you end up getting this as 4,096 over 3, which ends up being the same thing as 64 over 3, which is equal to about 21.3 feet. Right. So as long as you know the formula and what to plug into this formula here, at least for this example, it's not too bad, right? We were given a function that was pretty easy to integrate as it was just a polynomial. Any questions about this problem involving average value? Yeah, I would say usually the hard part, I mean, depending on the function that's given to you, it's just kind of like knowing how to compute the area. The area is kind of the hard part, or at least it can be the hard part. Okay, so it covers everything from section 15.2, which means we're going into 15.3. So this is where we start talking about triple integrals. Triple integrals, I mean, it's like one integral is bad enough, 2 is worse, and now we have 3. But at least we're going to stop here, okay? We're not going to go into quadruple integrals or, quintuple or anything like that. We're going to stop here at triple integrals. And then I guess really the rest of this class is going to be like, how do you compute triple integrals, and like how do integrals relate to like gradients and vector calculus and stuff like that. Which is like for the entirety of chapter 16 and 17. So triple integrals, like what we're doing now is we're mostly just going to be like, how do you create triple integrals? How do you compute them? And like, what do they measure pretty much? And so triple integrals, you should think of as being functions. Like you're going to have 3 integrals if you're looking at a function that has 3 variables. The number of variables you have determines the number of integrals that you need. So if you have like a function that is just in terms of x, use a single integral. If it's in terms of x, y, use a double integral. And then if you have 3 variables, you use a triple integral. And so these triple integrals of functions f of x, y, z of 3 variables are a fairly straightforward generalization of what we were doing with double integrals. And so what I mean by that is in single variable calculus, like you've had like an interval, right, that you're partitioning. For double integrals, you took a rectangle and you split it up into smaller rectangles. With triple integrals, you just look at the 3D analog of that. So you take a box and then you subdivide it into smaller boxes, right? So in the first most simple case, we're going to assume instead of a rectangle in the plane that we're looking at, our domain is going to be a box, which is really just a 3-dimensional rectangle. So we're going to be looking at domains of the following form, where it's just like a triple product of these 3 intervals. So this is really just saying we're looking at all of the points x, y, z in R3 such that x is bounded between a and b, y is bounded between c and d, and then z is bounded between p and q. So this is what our box looks like, right? Ignore like the partition, like all the sub boxes. Like this is the box that they're talking about. This is the product of the 3 intervals that we have, right? This is how you would draw it, right? So on the x-axis, we're going from A to B. On the y-axis, we're going from C to D. And then on the z-axis, we're going from P to Q. So it ends up giving you this box. Another way of thinking about it is this gives you, like we have like this rectangle, which is really like this part shifted downwards, right? So that's like this first product we had. And then when multiplying by this interval, we get this height with respect to z, which then gives you the box, right? So we have like the rectangle and then we give it like a 3rd dimension, which gives us the box. And so if we wanted to define a triple integral, so I don't go into as much detail in terms of like how these triple integrals are created. Like the main idea is you take these boxes, a box, you subdivide it into smaller boxes by creating partitions with respect to x, with respect to y, and with respect to z. Right, so we subdivide our box into sub boxes. Now we have to have 3 indices here. By choosing partitions of our 3 intervals, the volume of the box, this delta v, is going to be the product of each of these smaller lengths. And then what we do is from each of these sub boxes, we choose a sample point that we then feed into our function. And that'll give us some sort of like, I mean, technically it's like a 4-dimensional height, but we don't know how to like represent that or visualize that. So you just kind of have to understand conceptually what's happening. So we choose sample points from each of these sub boxes, plug it into our function, and then we look at the following triple sum. So this looks bad, but this is the last time you'll ever have to look at this. It's not like very valuable when doing computations. And so just like with single variable and triple integrals or double integrals, we have that this triple integral is going to be the limit as these partitions shrink of these triple sums right here. Right, so this gives you an approximation of what the triple integral is going to be. And then when you take the limit as the partitions shrink, so this becomes like the partition becomes finer and finer and you use smaller and smaller cubes, the triple integral ends up being exactly that. So you don't really have to, I mean, you should understand this, but I'm not going to ask you questions involving like compute this thing here and then do like the limit. We're not going to use like the definition very much, but I thought I'll give you some ideas like how these are constructed. And so these triple integrals have many of the same properties as double and single integrals. So they're going to be linear. So you can distribute these triple integrals over sums. And then you can also pull constants outside of these triple integrals. And these continuous functions are integrable over a box B. And then I guess like the main takeaway here, like this is how we're always going to be computing triple integrals, at least up until section 17 or chapter 17. The main point is that these triple integrals can be evaluated as iterated integrals. So it's like you can just compute them by doing the fundamental theorem of calculus 3 times in a row. So it's like it's just more work pretty much, right? At this point, like all it means is that you just have to do more integrals. So conceptually at this point, it's not terrible. You just have to compute 3 integrals is what it's really saying. And so just like in the double integrals, the order doesn't matter. So there's like this Fubini's theorem for triple integrals, which says that the triple integral of a continuous function, f of x, y, z, over a box ends up being equal to the following. Oh, okay. I was going to say, like, I was saying it doesn't, usually when they say Fubini's theorem, it's an indication that the order doesn't matter, but they say it here, like this iterated integral can be evaluated in any order. It doesn't matter if you do the integration with respect to z and then y and then x. You can also do it with respect to y first and then z and with respect to x. Like any of the 8 possible orders you can have here will give you the same integral at the end of the day. And then this shaded inbox is just saying that you can compute this triple integral one integral at a time, right? So this is like doing the integral of f of x, y, z with respect to z by treating x and y as constants. After you find that, you'll have a function in terms of x and y, and then you just have a double integral that you compute. Okay, so I mean, really it's just a matter of whether or not you understand how to do examples. Like, I'm not going to get really conceptual with the triple integrals. It's whether or not you know how to do examples pretty much. So the first example, it's like one of the more straightforward kinds of examples you can do. So we're doing a triple integral over the box B, where B is the box where the x values range from 1 to 4, the y values range from 0 to 3, and the z values range from 2 to 6. And then we're doing the integral of x squared times e to the y plus 3z. And so I need a, I don't know, these always take a lot of writing to go through, unfortunately. Right, so we have this triple integral of x squared and then e to the y plus 3z. Again, it doesn't matter what order you do these integrals in. I guess z is the new variable, so let's do it with respect to z first. Why not? Right, so we'll go the integral with respect to z first, and then y, and then x. So z ranges from 2 to 6. We have y ranges from 0 to 3. And then we have x ranges from 1 to 4. Right, and so for just ignoring like these first 2 integrals for now, and these other variables here, we just need to focus on what we have right now. So we're integrating with respect to z, which means we're treating x and y as constants. And so if we're integrating this function with respect to z, again, you just have to think in terms of what the antiderivative of this function is going to look like. It's going to end up being the following. So this is equal to the integral from 1 to 4, integral from 0 to 3. And so we have this 3 that's in front of the z. If you took the partial derivative of this function with respect to z, you would get a 1 over 3, or you'll get a 3 e to the y plus 3z. So we have to make sure like the 3 would be done away with. So we can have like a 1 over 3 here. And this would be x squared times e to the y plus 3z. You can also just use u substitution where u is equal to y plus 3z. If you do that, right, you would have du is equal to 3 dz, and then you divide both sides by 3, which is where this 1 over 3 comes from. But I didn't want to write out like the u substitution steps. You should feel somewhat comfortable just eyeballing what the antiderivative of this is. And so this is going from z is equal to 2 to z is equal to 6. You have dy, dx. And so you can kind of see this is going to get pretty tedious in that you plug in like z is equal to 6, to subtract by what you get when z is equal to 2. And now you have a double integral. So is this making the problems longer? Which is better than, I guess, making them really difficult conceptually, I guess, but it's a little bit tedious. Right, so I'm going to bring out the 1/3 outside of this actually. So this is going to be x squared, and then you're going to have an e plus y, or it's going to be e to the y plus 18, right? If you plug in z is equal to 6, you get 3 times 6, which will give you 18. And then this is going to be subtracted by what you get when you plug in z is equal to 2. So you'll have like a e to the y plus 6. I ran out of space, but there should be then like a dy dx here. All right, and so there's you can integrate it as is right here, but you can make things a little bit easier for yourself, right? You should remember that if you have like e to the y plus 18, this is the same thing as just doing e to the y multiplied by e to the 18, right? So you can write this as being e to the y times e to the 18, and then this is the same as like e to the y times e to the 6th power, right? I'm using, like if you have e, this is like something you may have seen a long time ago. If you have like e to the ab, it's the same thing as e to the a multiplied by e to the b. That's what I'm making use of here. And so you can rewrite this double integral in the following way. So this is 1/3 times the integral from 1 to 4 times the integral from 1 to 3. You have this x squared here. And so if you write it in this way, you can rewrite this as being e to the y multiplied by e to the 18 minus e to the 6th power, right? If you distribute it out, like if you did the product of these two things, you would get this right here. If you did the product of these two things, you would get this right here. The reason why you want to do this is now you can bring out the e to the 18 minus e to the 6th outside, because these are just numbers, right? They don't have anything to do with the actual variables. So you can rewrite this double integral as 1/3 times e to the 18 minus e to the 6th. And now it's just the double integral from 1 to 4, from 0 to 3 of x squared times e to the y. Right, so now we have a double integral, and we're masters at double integrals now, because we've gone through 2 sections on it. So this is 1/3 e to the 18 minus e to the 6th. Yeah, so if you do the integral with respect to y, it's not very interesting. It's just going to be e to the y over again. So this is going to be integral from 1 to 4, x squared times e to the y, evaluated from 0 to 3, dx. So you can see, I mean, we kind of know that we can do this. It just takes a lot of writing. It's kind of tedious. All right, so this is going to be the integral from 1 to 4. You have an x squared here, or x squared, not x cubed. If you plug in e is equal to 3, you get e cubed. If you plug in y is equal to 0, you get 1. Right, so you can bring out an e cubed minus 1. I'm not going to bother. I'm just going to integrate with respect to y. So this is 1/3 times e to the 18 minus e to the 6th, times e cubed minus 1. And then if you integrate with respect to x here, you get 1/3 times x cubed, evaluated from 1 to 4. Okay, and so what does this end up being equal to? This ends up being equal. So I plug these numbers in. On the exam, you can leave your answer like this. You don't have to plug in. You've already gone through enough work, I guess. I sympathize with you. So this is e to the 18 minus e to the 6th. And then this will be times e cubed minus 1. And I guess you could determine what these numbers are, but I'm just going to leave it as is. Like e to the 18 is a huge number. So this is much more concise and is less writing at the end of the day. So you can see, like conceptually, this shouldn't have been too bad, right? It's just like a bunch of integrals you know how to do, but there's just a lot of busy work, right? Because you're just doing 3 integrals at the end of the day. And one is alone. One alone can be a lot of work. So now you have to do 3 in a row. Which is why no one likes triple integrals, but you have to know, unfortunately. Okay, any questions about this example? And we'll have tools later on that are kind of akin to the fundamental theorem of calculus, where we'll be able to think of triple integrals as being special kinds of like double integrals. And we'll develop some tricks later on that'll make these computations nicer in the future, assuming you understand the tricks. Otherwise, it's just going to look really confusing. Okay, yeah, so we did it over the simplest kind of domain that we can have, right? We just integrated over a box. This is kind of like, well, we know how to do integrals over rectangles. Like, what about more general regions? So that's what this next part is going to be talking about. So in order to integrate over more general regions for double integrals, we looked at regions that were vertically simple and horizontally simple. We're going to do pretty much the exact same idea here, except now we're going to be thinking in terms of the third dimension. So we're going to be looking at surfaces or regions that are Z simple, which isn't as nice a term, but I don't know what else you would call it, right? So what does it mean for a function to be Z simple? It just means that Z, which is f of x, y, z. So maybe I should write that out. So we're assuming Z is equal to like some function f of x, y, z. We're saying that it's bounded between two functions, like in this picture. So this is like our Z1. And this is our Z2. Right? And so the main point is no matter what we have, when like every single point within our region W is bounded between Z1 and Z2, right? So if you start at Z1 and you go upwards, it always finishes at Z2, like the upper bound is given by Z2. And so if you have such a Z simple region, the triple integral over this three-dimensional region here can be seen as the following iterated integral. So this triple integral over this 3D region is equal to the following iterated integral. So you have your double integral over D, right? If it's a double integral, it means you're out over the XY plane, like a 2D region of the XY plane. And then the third integral corresponds to like this third dimension that we have here, right? So the upper bound is given by Z1, the lower bound is given by Z1, and then the upper bound is given by Z2. And so this is a function of two variables. This second integral is going to be bounded by a function of a single variable. And then the final integral will be just in terms of constants, right? So for every integral from the innermost to the outermost, you're always losing one variable in your bounds. That's something important to remember. It's like something a lot of students in my class last semester was tricked up about. So like, for instance, like this next bound could be like G1 of X, G2 of X, but it's not going to be like G1 of XY, G2 of XY, like it's just in terms of a single variable. And then this last one would just be in terms of like constants. Right? I mean, we'll see this in examples, but it's something you need to keep in mind. And I'm rambling on about this, but I want to make sure people understand it. Like it should make sense, right? If you have a triple integral, that means you're playing with three variables. Once you're working with like two integrals, that means that you're working with like two variables, X and Y. So that means like the bounds should just at most have one variable. And then after you're done with that and you're just left with a single integral, you're back in calculus 1 territory. So the bounds should just be numbers. Like you never had like bounds that were functions in calculus 1. Okay, so let's go through examples. So again, this is kind of what you need to be able to do on the midterm is I'll ask you to do at least one triple integral straight up, where I just give you a region and tell you to integrate over it. And so what it wants you to do with this example is it wants you to evaluate the triple integral over this three-dimensional region W. So W is the region bounded between these two planes here. Right, so W is the region bounded between the plane Z is equal to X plus Y and the plane 3X plus 5Y here. And then it's lying over the rectangle given by D is equal to 0, 3 crossed with 0, 2. So that's this rectangle right here. Right, so when we're doing these triple integrals, like we're not finding the volume between these two planes. We're saying this is the actual region we're integrating over. Technically, this triple integral is going to give you something called like hypervolume, which is like the volume of a It's like 4-dimensional shape. Not that we know like those exist or anything like that, but the actual like application of triple integrals is to find like mass and density. Usually, like that's how it's used in physics, or like charge, which we'll see later on. Okay, so how do we compute this triple integral? The first thing we take note of is that it's going to be z simple due to the fact that the lower bound is given by x plus y, and the upper z bound is given by this 3x plus 5y. So we can write out this triple integral over w. So this is z dv. We can write it out. So I'm going to mimic how they wrote things out in this theorem right here. So I'm just going to say this is equal to the double integral over d, this region, this rectangle that we have here. And so this covers the x and y variables. We're just left with the z variable, which is going to be this integral right here. So this is going to be z, and then this is going to be dz, and then outside we're going to have like dA. This is corresponding to like dx, dy, right? I'm just imitating what they're doing here. So I think it's a good way of writing it out and organizing. And so we have to think in terms of like what z ranges from. So as I've been saying over and over again, the lower bound is given by x plus y, and the upper bound is given by 3x plus 5y. And so, I mean, I think it's a nice way of writing this out because we can kind of just ignore everything outside of the parentheses for now, and you just have a single variable integral, right? And so this is just going to be equal to the double integral over d of 1/2 of z squared, and it's going to range from x plus y to 3x plus 5y. And then you have like this dA right here. And so we can bring out the 1/2. This is going to be 1/2. You still have like this double integral over d. You have z squared ranging from x plus y to 3x plus 5y. And then you have this dA. And so after we plug in these bounds of integration, and for z, we'll just be left with the function with respect to x and y, and we'll have a double integral that we can then compute, right? So this is going to be equal to 1/2 times this double integral. Yeah, so what does this end up being equal to? So if you plug in, I'm just going to write out what happens. So if you plug in 3x plus 5y and for z squared, and then you subtract by what you get when you plug in x plus y into z squared, this ends up being equal to the following. So this ends up being this double integral over d. So if you plug these quantities in, this gives you 4x squared plus 14xy plus 12y squared dA. And so now we just need to compute this double integral, right? And this double integral is just over d, right? Where d is this rectangle. So we just go back to what we did in section 15.1 at this point. Like we've covered kind of like the triple integral part with respect to z, and now everything is in terms of x and y. So I'm just going to take this, I'm going to erase this d here, and I'm going to change dA. And so I'm going to integrate first with respect to y, and then with respect to x. And so we know y ranges from 0 to 2, and x ranges from 0 to 3. And so now it's just a matter of computing this double integral. So I might go through this a little bit quickly here. So you do the integral with respect to y. If you do the integral with respect to y, this is going to be the integral from 0 to 3. You have a 4x squared y plus 7xy squared plus 4y cubed ranging from 0 to 2 dx. If you plug in y is equal to 2, subtract by what you get when you plug in y is equal to 1, you get the integral from 0 to 3 of 8x squared plus 28x plus 32 dx. And then if you compute this integral, this is just going to be 8 over 3x cubed plus 14x squared plus 32x, going from 0 to 3. And then if you plug in x is equal to 3 into this, you end up getting this is equal to 294. Right, so I kind of went through it quickly, but I mean, once you're at this point, you're in familiar territory. Like the big part that was new was this part right here, right? It's like the third integral corresponding to z. But yeah, once you're here, it's kind of smooth sailing, aside from just like plugging in numbers and putting things into the calculator correctly. Any questions about this example? Yeah.
The second line, when we took out like the half, did you like put it back?
I believe I did. I'm not gonna lie. I wrote out these notes last semester and I didn't check to see. There might be a 1/2 that's in front of all of this. Is that what you're saying? Like there should be like a 1/2. I'm seeing people nod, so you're probably right, to be honest. Yeah, I think there might still be like a 1/2 in front of that. And then this would be like over 2. Okay, yeah, so just like a constant. Okay, any other questions about this one? Okay, yeah, so this next example is pretty much the exact same thing over again, right? So it wants you to evaluate this triple integral W. We have the same upper bound for Z, and we have the same lower bound for Z as well. And we're integrating over Z. The only thing that changes is the values of X and Y that we're taking into consideration, right? Before, we were looking at this rectangle, and now we're looking at this triangle. So at least in the beginning, this isn't going to make that much of a difference, right? So you're still going to have, like if we want to do this triple integral over W of Z dV, this is still just going to be equal. So you have this double integral over D, where D is this triangle here. And then you have like this third integral here bounded by X plus Y, and then 3X plus 5Y. And then we're integrating Z. This will be dz, and then you'll have the dA. And so this is exactly the same as what we had before, right? There's no difference between what we have here and what we have here. The only thing that's going to change is the double integral. So we already know that this is going to be equal to this 1/2 times this double integral over D of 4x squared plus 14xy plus 12y squared dy dx, right? So it's exactly the same as what we had here. The only thing that's going to change now is the bounds that we have for this double integral. Oh, I kind of already wrote things out in terms of dy dx, but whatever. Yeah, so we need to determine what these bounds of integration are going to be. So I guess I'll just say we're going to integrate with respect to y first, and then we'll integrate with respect to x. And so if we want to integrate with respect to y first, what we need to do is we need to determine the bounds with respect to y, right? So if you start here, so we can already see we have a lower bound with respect to y on this domain given by y is equal to 0. And you can see this is vertically simple, right? Because we start at y is equal to 0, and then we go up until we hit this line right here. This line here that I'm highlighting in red. And so we just need to determine the equation of this line that I'm circling, right? Does anyone know, like, what is the equation of this line going to be? Yeah, go ahead. It's not going to be, it'll be y is equal to 1 minus x, right? This is like, if you look at this equation, like ignoring all like the 3-dimensional junk that's happening up here, and just thinking in terms of the xy plane, we have something like this, right? This is really what our region D looks like. So it starts, we have like y is equal to 1 here, we have x is equal to 1 here, and then we have this line here. Right, so this is a line segment where the y-intercept is given by 1. And then the slope is given by 1, because if you go 1 unit to the right, like you end up intersecting with the x-axis. So this ends up being y is equal to 1 minus x. That's so these two things, what I'm highlighting in red here and what we have here, these are the exact same line, right? So this is the line, y is equal to 1 minus x. So that'll serve as the upper bound with respect to y. And then with respect to x, is this going to be some constants, right? And so we know that x ranges from 0 to 1. So we just have 0 to 1 here. Okay, and so now you compute this integral as we did before, right? So nothing really changes all that much, aside from what we're eventually going to be plugging into the antiderivative. So this is going to be 4x squared y plus 7xy squared plus 4y cubed from 0, kind of looks like a 6, from 0 to 1 minus x dx. And then you plug those terms in. I'm kind of tempted to just kind of skip all this. So this is 0, 1. This ends up being 4 minus 5x plus 2x squared. Oops, 2x squared minus x cubed dx. And then you integrate this thing with respect to x. This is like 1/2 of 4x minus 5 over 2x squared plus 2 over 3 times x cubed minus 1 over 4 x to the 4th power, evaluated from 0 to 1. And so you end up getting this, it's going to be, I had 23 over 12 written here, but maybe it should be 23 over 24 instead. I don't know. The constant, I should have reworked this before I did the lecture, but what matters is, you know, like the steps and the principles. So it might be off by a constant. I don't know. I'll check through after class to make sure. But yeah, like the main thing is like, you know how to and do the same step over as before, but now you have this thing going on, right? You know how to get like this 1 minus x. It's like the big thing. Any questions about this example? Okay, and I mean, these are kind of like this kind of problem. I think this was the problem. I chose something similar to it on the second midterm. So if you can do this one, you're in pretty decent shape. I mean, I could ask for one that's a little bit more difficult, I suppose, but I don't know if I will or not. Let's see. Let's ignore this next example here. Instead, we'll focus. Oh, I chose. Oh, there's another example I wanted to do that's not on here. Oh, I see what happened. The picture's incorrect. Okay, yeah. I'll make an adjustment. We'll go over this one on Monday of next week. I wanted to go over it today, but this is not the right picture. It should be a different picture, and it's a very difficult picture to draw. So wait, let me see if I mean, you wouldn't have it in front of you, but this is what it should look like. I should have the notes from last semester here. Yeah, this is what the picture should look like, not like the dinky triangle that you have. Wait, is this what yours looks like? Oh, you have the triangle. Never mind. Okay, so I'll send you another. Like on Monday, I'll print something else off that has like this picture. This is what it should look like. It shouldn't look like the triangle. So let's just look at average value before we end class. And then we'll go over the example from page 10 on Monday. Yeah, so just like we were doing before in the beginning of class today, you can look at the average value of a function in terms of 3 variables, again, by considering a triple integral. And so, like I was saying in the beginning of class today, this is something that's important, right? We have b minus a. This is equal to like the length of an interval. This is equal to the integral of 1 from a to b dx. We found that the area was equal to this double integral. Let me say this, like the area of a region D is equal to the double integral of 1 over the region D, dA. And then what also ends up holding true, if you think over a box, right, is that the volume of this 3-dimensional region W is going to be equal to the triple integral over 1, or the triple integral of 1 over W dV, right? The idea is like if you're integrating over a box, right, you'd be integrating 1, and this would be like AB, this would be CD, and this would be PQ. And so this would end up being equal to B minus A multiplied by D minus C multiplied by Q minus P. And this would be equal to the volume of the box determined by like these 3 intervals right here. So this is something that you should, I mean, we're not going to see it too much at the moment, but it's something we'll see much more frequently later on. The main idea is if you're just integrating 1, right? Like you're kind of like, this is like change in area. So if you integrate 1, like the integrals in a sense just end up giving you like the area. And if you integrate 1 over a 3D region, like it ends up just giving you like the volume here. And eventually we'll be integrating over arc lengths, and we'll see like if you do like a path integral with respect to an arc length, they'll end up giving you like the arc length. And so this volume equation, like this average value of a function of 3 variables, like it's defined in a familiar way. And so this, in the sense that it's like 1 over the volume of W multiplied by this triple integral of f of x, y, z. But you can rewrite it in the following way. I mean, I already tell you like the volume's equal to this triple integral, but you can rewrite it as the following quotient. So this is the triple integral over W of f of x, y, z dv. And then this is over the triple integral over W of 1 dv. Right, because like volume of a general region is hard to find. Like usually you're not going to be able to just like look at the surface and determine, or like the region and immediately be able to determine what the volume is going to look like. Right, so like for instance, in this next example, right, like this next example, what it's going to want you to do is it tells you that a solid piece of crystal W in the first octant of a space is bounded by the 5 planes given by z is equal to 0, y is equal to 0, x is equal to 0, and then you have x plus z is equal to 1, and then x plus y plus z is equal to 3. So it says that the temperature at every point in the crystal is given by the following function in degrees centigrade, and it wants you to find the average temperature for all points within the crystal, right? And so it'd be hard to just like look at the region we're taking into consideration and be able to determine the volume just by looking at it. So you would want to be able to express it as a triple integral. And so where we'll leave off is we're just going to find the bounds of integration of the region that they describe here. And then we'll finish this example on Monday of next week, right? So we know some information. So in order to find the average value of f, we had to have like a triple integral. And so it tells us here that we always have z. It's bounded below by z is equal to 0, y is equal to 0, and x is equal to 0. So we always have 0 is less than or equal to x, is less than or equal to something. We always have 0 is less than or equal to y, is less than or equal to something. And we always have at 0 is less than or equal to z, is always less than or equal to something. And so now we need to determine what these upper bounds are going to be. And so what I would recommend, I think this is actually close to the problem I asked on the second midterm last semester. It's like kind of give you a description of these variables and how they relate to one another. And so the way of thinking about this is we have a way in which we can relate x and z with one another in terms of just 2 variables. So you should be thinking that like this x plus z is equal to 1 is going to be a bound on the second integral, like the middle integral, like this one right here. And the only way in which we can relate y with x and z is when we have both variables involved, right? Like we have x plus y plus z is equal to 3. So the thinking is like, if we're involving 2 variables and are bound, that means it's going to correspond to this integral that we have here. It's like for every integral you move leftwards, like you lose a variable. So this is like 2 variables. This is 1 variable. This is 0 variables. And we only know how to relate y in terms of 2 variables. So let's say like y is less than or equal to 3 minus x minus z. So I'm just taking this equation and solving for y. And then with respect to z, we can just look at this equation, right? You can subtract x by both sides, and so you get z is less than or equal to 1 minus x. And then the final bound is just going to be y is equal to 1, or x is less than 1, right? Like if you added these three things up, it has to be at most 3. And if you add these two, like if z is equal to 0, that means x has to be equal to 1, and that's as large as x can be. Right, so these are the 3 bounds of integration. It's 12:50 now, so I'll stop here. But this is what we'll pick up in class on Monday. We'll actually go through and find what the average value is going to be.